An object from another star system rushes toward the most critical point of its journey through our cosmic neighborhood. And everything we thought we understood about visitors from the void hangs in the balance. This isn't science fiction speculation or wishful thinking about alien contact manufactured from ambiguous data and desperate hopes. This is physics, playing out in real time across millions of kilometers of interplanetary space. Observational astronomy pushed to its absolute operational and theoretical limits. And humanity, standing at a threshold where the next few days of systematic data collection and rigorous analysis could fundamentally reshape our understanding of whether we're truly alone in this vast universe, or whether intelligence is a common emergent property of cosmic evolution. The visitor carries a designation that sounds clinical and bureaucratic, deliberately stripped of emotional content, but masks something profound lurking beneath the alphanumeric code. The International Astronomical Union assigns these designations according to strict conventions developed over centuries of astronomical practice, creating systematic naming schemes that encode discovery circumstances and orbital characteristics. 3I Atlas represents the third confirmed interstellar object, the slash indicating interstellar origin. Atlas referencing the asteroid terrestrial impact last alert system that first detected this wanderer during routine sky surveys designed primarily to find potentially hazardous asteroids threatening Earth, rather than extrasolar visitors racing through on one-time trajectories. This object races through our solar system on a hyperbolic trajectory that mathematical analysis confirms will carry it through our cosmic neighborhood exactly once, before departing forever into the interstellar darkness from which it emerged. Hyperbolic orbits represent a specific mathematical category of trajectories characterized by eccentricity greater than 1, meaning the object possesses more than enough velocity to escape solar gravity permanently. Unlike elliptical orbits that characterize planets, asteroids, and short-period comets gravitationally bound to the Sun in endless repetition, hyperbolic trajectories are one-way tickets. Visitor passes, allowing brief passage through our stellar domain before ejection back into the void separating stars. Let's establish the stakes with absolute clarity and precision before diving into complex mechanisms and elaborate scenarios that might unfold during these critical days. This object approaches its closest point to the Sun, what astronomers term perihelion, from Greek roots meaning near the Sun, traveling at speeds that betray its extrasolar heritage through simple Newtonian mechanics applied to measured velocities. The excess velocity measures approximately 60 kilometers per second relative to the Sun's rest frame, far too fast for anything gravitationally bound to our star through normal planetary formation processes. Natural objects born within our solar system, even those on the most extreme elliptical orbits stretching to the Oort cloud's outer boundaries, possess orbital velocities determined by conservation of energy in the Sun's gravitational field. That speed differential tells us everything essential about this visitor's origins with mathematical certainty that admits no ambiguity, regardless of what compositional or behavioral oddities might complicate interpretation. This object was born somewhere else, ejected from another stellar system light years distant through gravitational interactions we can model theoretically, but have never directly observed in action. The physics of planetary system formation inevitably produces debris ejection as protoplanets gravitationally scatter smaller bodies during the chaotic epochs when solar systems condense from rotating molecular clouds. Most ejected material carries insufficient velocity to escape the birth star's gravity, falling back in elongated ellipses or crashing into planets. But statistical mechanics guarantees that some fraction receives just the right gravitational kicks during close planetary encounters to achieve escape velocity, launched on interstellar trajectories carrying them away from their birth systems forever. These natural wanderers likely number in the trillions throughout the galaxy, ancient debris from planetary formation epochs spanning billions of years across hundreds of billions of stellar systems. Most drift through interstellar space indefinitely, cold and dark, invisible against the cosmic background, until random gravitational perturbations from passing stars alter their trajectories. Occasionally, purely through statistical chance operating over galactic timescales, these wanderers pass through other stellar systems, temporary visitors on hyperbolic flyby trajectories. Earth-based surveys finally possess sufficient sensitivity to detect these rare events, transforming interstellar visitors from theoretical predictions into observed reality during the past decade of rapid astronomical capability advancement. The geometry of 3I Atlas Perihelion passage creates a frustrating observational nightmare that tests the limits of what modern astronomy can achieve, even with our most sophisticated space and ground-based instruments. During the critical hours when this visitor swings closest to the Sun, experiencing maximum solar heating and potentially executing any maneuvers if artificial propulsion systems are present, it sits in solar conjunction from Earth's perspective. This means it appears too close to our star's overwhelming brightness for direct observation, using conventional techniques, creating an enforced blackout period precisely when observations matter most for distinguishing natural from artificial behavior. Ground-based telescopes become completely useless during solar conjunction, because pointing them anywhere within several degrees of the Sun risks catastrophic, permanent damage to sensitive instruments and poses severe danger to human eyesight. Solar radiation concentrated by telescope optics onto instrumentation designed for faint object detection would instantly destroy detectors calibrated for photon-starved deep space observations. Professional observatories maintain strict pointing restrictions, preventing telescopes from slewing anywhere near solar positions. Automated safety systems refusing commands that would violate these limits regardless of scientific justification. Amateur observers face even greater risks attempting solar observations without specialized equipment specifically designed for that purpose. Space-based coronagraphs offer partial solutions, designed specifically to block solar glare through precisely positioned occulting disks that create artificial eclipses, allowing study of the faint corona normally invisible against the photosphere's overwhelming brightness. These instruments routinely observe comets passing near the Sun, capturing thousands of sun-grazing comets over decades of operation. However, coronagraphs possess limited fields of view, extending only a few solar radii from the star's center, and 3I Atlas passes just beyond this effective range during closest approach. We're essentially flying blind at precisely the moment when observation matters most, dependent on observations before and after conjunction to infer what occurred during the hidden hours. This blackout period isn't unusual or suspicious, merely an unavoidable consequence of physics and geometry affecting any object passing near the Sun from Earth's perspective. Observational gaps are an accepted frustration of astronomy, built into the fundamental limitations of how we detect faint objects against bright backgrounds using instruments operating at the thermodynamic and quantum noise limits. Professional astronomers understand and routinely work around these limitations, planning observation campaigns that maximize data collection during accessible windows, while accepting that some information remains permanently beyond reach. But the timing of what might unfold during these hidden hours carries implications that extend far beyond routine astronomical cataloging and natural object characterization. If this object represents merely a natural comet, an interstellar iceberg wandering through space following purely gravitational physics, then perihelion represents a predictable, well-understood physical process that planetary scientists have studied for centuries through observations of solar system comets. Solar heating drives sublimation of volatile ices locked within the nucleus, transforming solid material directly into gas, without passing through liquid phase in the vacuum of space. This sublimation releases molecules into the surrounding space, creating the characteristic glowing coma and extended tail that define cometary appearance. The trajectory during and after perihelion would follow gravitational physics, with only small perturbations from asymmetric outgassing that acts like tiny rocket engines distributed unevenly across the rotating nucleus. These non-gravitational forces represent well-characterized phenomena in cometary science, understood through detailed physical models and confirmed through decades of spacecraft observations of solar system comets. The magnitude and direction of these forces depend on rotation rate, nucleus shape, volatile distribution, and thermal properties of surface materials. Sophisticated computer simulations can predict these effects with reasonable accuracy, allowing astronomers to distinguish expected natural perturbations from anomalous accelerations requiring exotic explanations. But if this visitor carries technology, if it represents an engineered artifact rather than a natural object shaped purely by accretion and random collisions, then perihelion becomes something entirely different and profoundly more significant. It becomes the optimal moment for deliberate action, the precise window when any applied thrust yields maximum efficiency through orbital mechanics principles that any civilization capable of interstellar travel would understand intimately and exploit ruthlessly. Velocity peaks during closest approach to the Sun according to Kepler's laws and conservation of angular momentum, and kinetic energy scales with the square of velocity, meaning even modest thrust applied at this moment produces disproportionately large changes in total orbital energy. A spacecraft designed to alter its trajectory for rendezvous with inner solar system destinations, or to modify its departure path as it exits back toward interstellar space, would logically execute major maneuvers during this perihelion window. The efficiency gains are simply too large to ignore for any mission planner working with finite propellant budgets and energy constraints. This principle, known technically as the Oberth effect, after Hermann Oberth, who described it mathematically in early 20th century rocketry literature, represents fundamental orbital mechanics accessible to undergraduate engineering students. Any intelligence capable of building interstellar probes would grasp this concept immediately and design mission profiles exploiting it fully. The mathematics supporting this reasoning are straightforward, elegant, and utterly undeniable once you work through the derivations carefully. Consider the energy budget for changing velocity in different gravitational and kinetic energy regimes. The kinetic energy change equals 1/2 times mass times the change in velocity squared. But this simple formula masks deeper complexity when objects operate in gravitational fields. Burning propellant to change velocity while moving slowly through weak gravitational regions produces modest increases in total orbital energy. But executing that same velocity change while moving rapidly through strong gravitational regions, like the intense field near the Sun during perihelion, multiplies the orbital energy change dramatically through nonlinear coupling between kinetic and potential energy. Apply thrust when you're moving slowly far from the Sun, and you get a modest energy boost. Apply identical thrust when you're screaming past the Sun at maximum velocity, and the energy benefit increases by factors that can reach 10 or more depending on specific orbital parameters. This isn't speculation or exotic physics requiring new theories. It's basic orbital mechanics taught in undergraduate aerospace engineering courses worldwide. The same principle that allowed spacecraft like Voyager to steal momentum from Jupiter and Saturn during gravitational assists, multiplying their velocity changes far beyond what onboard propellant could achieve through simple thrust in empty space. Any intelligence capable of building interstellar probes would understand this principle intimately, incorporating it into mission design from the earliest planning stages. The efficiency gains are too substantial to ignore when working with the enormous energy budgets required for interstellar travel. Even civilizations far more advanced than us, with access to propulsion technologies we can barely imagine, would still face fundamental physics constraints on energy and momentum. Why waste resources executing maneuvers inefficiently when orbital mechanics provides free energy multiplication through proper timing? The logic is inescapable for any rational actor operating within known physics. The tension between headline speculation and scientific caution has never been greater or more apparent in public discourse surrounding this visitor. Media outlets have run stories for weeks suggesting dramatic possibilities, with headlines screaming about humanity's potential first encounter with alien technology, despite absence of definitive evidence supporting such extraordinary claims. Avi Loeb, the Harvard astronomer who famously and controversially argued that Oumuamua might represent artificial technology rather than natural asteroid, has weighed in with provocative public statements about unusual chemical signatures detected in spectroscopic observations of 3I Atlas. These statements receive amplification through social media platforms optimized for engagement rather than accuracy, creating information cascades where speculation spreads faster than careful qualification. Public warnings have circulated online through various channels, some claiming institutional cover-ups by governmental and scientific authorities deliberately hiding evidence of extraterrestrial contact. Others suggesting that classified observations reveal far more than public statements acknowledge. These conspiracy narratives flourish in information environments where trust in institutions has eroded, and where confirmation bias leads people to interpret ambiguous evidence as supporting pre-existing beliefs about government secrecy and hidden truths. Meanwhile, the mainstream professional astronomical community urges restraint, reminding everyone through official statements and press releases that extraordinary claims require extraordinary evidence, and that we've been fooled by natural phenomena mimicking artificial signatures many times throughout scientific history. The pulsar discovery in 1967 provides a cautionary historical example of how genuinely novel natural phenomena can temporarily appear artificial, until proper physical understanding emerges through careful theoretical work. When Jocelyn Bell Burnell first detected regular radio pulses from celestial sources, the discovery team half-seriously labeled the signals LGM1, standing for Little Green Men. Acknowledging the possibility that these precisely timed emissions might represent artificial beacons from extraterrestrial civilizations attempting interstellar communication. Only after identifying multiple pulsars with different periods and establishing that their locations match supernova remnants did the natural explanation emerge. Rapidly rotating neutron stars with intense magnetic fields, generating lighthouse-like beams of radio emission, sweeping past Earth with clockwork regularity. That episode demonstrates how genuinely revolutionary discoveries of new natural phenomena can temporarily mimic artificial signatures, until scientists develop adequate theoretical frameworks explaining observations through natural physics. The lesson applies directly to interpreting anomalies in interstellar visitor behavior and composition. Unusual doesn't automatically mean artificial. Nature produces surprises regularly, exhibiting phenomena that don't fit existing models because our models remain incomplete, rather than because observations genuinely defy natural explanation. Distinguishing between these possibilities requires patience, careful analysis, and willingness to consider multiple competing hypotheses simultaneously, without prematurely committing to extraordinary interpretations that might prove embarrassing when mundane alternatives eventually emerge. Navigating this territory requires intellectual honesty about uncertainty while still taking the questions seriously enough to pursue rigorous investigation, rather than dismissing them reflexively. The default position in science demands skepticism toward extraordinary claims, a conservative bias that protects against chasing every anomaly down speculative rabbit holes that waste resources and distract from productive research directions. This conservative instinct serves important institutional purposes that shouldn't be dismissed lightly. It prevents waste of finite resources on pseudoscientific dead ends that promise revolutionary breakthroughs but deliver only confusion and embarrassment. It maintains rigor in standards for what counts as credible evidence versus mere speculation dressed in scientific language. It protects the hard-won reputation of scientific institutions as reliable sources of knowledge, rather than platforms for promoting unverified wild ideas. But conservatism carried too far can also systematically blind us to genuine novelty, causing reflexive dismissal of observations that don't fit existing frameworks simply because they challenge comfortable assumptions about how nature operates. The history of astronomy includes multiple sobering examples where phenomena initially dismissed as impossible or irrelevant by mainstream scientific consensus eventually revolutionized understanding once a few persistent researchers finally took them seriously enough to investigate properly, despite professional skepticism and career risks. Continental drift in geology faced decades of ridicule before plate tectonics emerged as a unifying theory. Meteorites were dismissed as folklore and delusion until careful documentation forced acceptance. Quasars puzzled astronomers because their properties violated theoretical expectations about energy generation, until supermassive black hole accretion provided natural explanation. The challenge involves finding appropriate balance between these opposing risks: premature acceptance of exotic explanations versus premature dismissal of genuine anomalies. Neither extreme serves truth well. Believing every unusual observation indicates alien technology produces noise-overwhelming signal, boy who cried wolf dynamics that eventually prevent recognition of actual contact when it finally occurs. But dismissing every anomaly as measurement error or misunderstood natural process guarantees missing revolutionary discoveries, until accumulating evidence becomes so overwhelming that resistance collapses, often decades later than optimal for scientific progress. Threading this needle requires intellectual humility. Acknowledging our understanding remains incomplete. Rigorous methodology, distinguishing genuine anomalies from artifacts, and cultural environments where asking uncomfortable questions doesn't automatically trigger professional ostracism. So, what exactly would constitute evidence strong enough to elevate 3i Atlas from interesting natural comet worthy of scientific study to genuine technological artifact, requiring complete revision of humanity's understanding of our place in cosmic order? The answer involves specific observational signatures that natural objects simply cannot produce through any plausible combination of known physical processes operating within established theoretical frameworks. First and most definitive would be non-gravitational acceleration exceeding what cometary outgassing can explain, even under maximally generous assumptions about volatile composition, rotation rates, and nucleus properties. Comets experience small trajectory perturbations, as sublimating gas escapes preferentially from specific regions of rotating nuclei, creating thrust that acts like arrays of tiny rocket engines distributed unevenly across the surface. These natural rocket forces are modest in magnitude, typically producing accelerations measured in millimeters per second squared, and they follow predictable patterns based on rotation state, nucleus shape and composition, volatile distribution, and heliocentric distance determining solar heating intensity. An object accelerating beyond these natural limits through forces pointing in directions inconsistent with solar radiation pressure or outgassing geometry patterns would demand explanation through mechanisms beyond passive response to environmental conditions. Active propulsion systems, deliberately altering trajectory through controlled thrust, represent the most straightforward explanation for accelerations exceeding natural cometary forces by significant margins, particularly if those accelerations exhibit timing and direction, suggesting optimization for specific orbital objectives rather than random outgassing patterns. Second would be electromagnetic emissions with characteristics indicating artificial origin rather than natural thermal or spectral line radiation. Natural objects emit thermal radiation following Planck's blackbody law, spectral distributions determined purely by temperature through fundamental thermodynamics that admits no exceptions within classical physics. They might also emit spectral lines from specific atoms or molecules undergoing electronic or vibrational transitions. But these natural emissions follow quantum mechanical rules, with characteristic wavelengths and intensity ratios determined by atomic physics and molecular chemistry. Artificial sources can produce fundamentally different emission patterns, structured signals with deliberate modulation encoding information, coherent electromagnetic radiation at discrete frequencies chosen for maximum transmission efficiency through interstellar or interplanetary medium. Polarization patterns impossible for natural thermal sources. Radio telescopes monitoring 3I Atlas during perihelion and subsequent departure could detect such emissions if they exist, distinguishing them from natural background through sophisticated statistical analysis of signal characteristics. The search for extraterrestrial intelligence community has developed extensive methodologies for this purpose over decades of scanning for artificial signals from distant stars. Narrow bandwidth emissions concentrated in frequency ranges where natural astrophysical backgrounds minimize interference, frequency drift patterns compensating precisely for relative motion between source and observer, modulation schemes carrying information content through amplitude, frequency, or phase variations, all represent signatures difficult or impossible to produce through natural astrophysical processes, but straightforward for technological transmitters to generate deliberately. Third would be geometric structure visible in high-resolution imaging that proves inconsistent with natural formation through accretion and random collisions. Comets and asteroids exhibit irregular shapes produced by gravitational aggregation of material during solar system formation, followed by modification through impact cratering and structural failure. These natural shapes show randomness inherent to processes governed by statistical mechanics rather than deliberate design. Spacecraft require geometric precision for functional purposes. Planar surfaces for solar panels or radiators, cylindrical or spherical pressure vessels, structural elements arranged in regular arrays serving specific engineering functions rather than natural chaos. High-resolution optical imaging could reveal such features if present, distinguishing artificial geometry from natural irregularity through statistical analysis of surface curvature, edge straightness, and structural regularity. However, achieving sufficient spatial resolution to detect these geometric details presents enormous technical challenges, given the distances involved during accessible observation windows. At ranges of millions of kilometers, resolving features smaller than hundreds of meters demands either impossibly large telescopes or proximity achieved through dedicated interception missions. Current ground-based instruments operating at diffraction limits can barely resolve 3I Atlas as anything beyond point source, preventing detailed shape characterization. Space-based platforms like Hubble possess better resolution but still struggle with fast-moving targets at solar system distances. Only dedicated spacecraft missions achieving close flyby or rendezvous could provide imaging resolution sufficient for definitive geometric analysis. Missions that require years of preparation and cannot be organized rapidly enough to catch fleeting interstellar visitors. Fourth would be thermal signatures incompatible with passive solar heating, following straightforward thermodynamic equilibrium. Natural objects exposed to sunlight warm according to simple energy balance, where absorbed solar radiation equals thermal emission to space, reaching equilibrium temperatures determined by heliocentric distance, albedo, thermal conductivity, and rotation rate. The temperature distribution across natural object surfaces follows predictable patterns. Subsolar point hottest, where illumination concentrates. Terminator regions cooler. Night side coldest. Active technological systems generate internal heat from onboard power sources, like nuclear reactors, radioisotope thermal generators, or other energy conversion systems, creating thermal anomalies that infrared sensors could detect. Temperature gradients oriented incorrectly relative to solar illumination geometry. Localized hotspots where physics predicts they shouldn't exist based on passive heating models. Thermal emission intensities exceeding what solar absorption can supply. All would flag active thermal management systems, operating through mechanisms beyond simple radiative equilibrium. Advanced infrared telescopes operating across multiple wavelength bands can measure these temperature variations with precision, constructing detailed thermal maps revealing whether observed heat distribution matches natural expectations derived from well-validated thermodynamic models, or indicates something fundamentally different, requiring explanation through internal power generation and deliberate thermal control. Fifth would be systematic changes in activity level or brightness that correlate poorly with heliocentric distance, or show variations too rapid for thermal processes to explain naturally. Cometary outgassing intensifies predictably as objects approach the sun, and solar heating strengthens, then diminishes symmetrically during departure as the comet cools and volatile sublimation rates decrease. This creates characteristic brightness curves symmetric around perihelion that planetary scientists can model quantitatively using established thermophysical theory. Objects that brighten or dim on schedules unrelated to solar distance, or that exhibit activity variations occurring on timescales of hours when thermal response time should measure in days, might be executing deliberate operational changes, rather than responding passively to changing environmental conditions through purely physical processes, governed by heat diffusion and volatile sublimation kinetics. None of these signatures alone would prove artificial origin beyond all reasonable doubt, because nature occasionally produces surprises, and our theoretical models, however well tested, remain approximations of reality rather than perfect representations. Unusual acceleration might result from asymmetric outgassing in unexpected geometric configurations we didn't anticipate. Electromagnetic emissions could arise from plasma physics phenomena we don't fully understand, operating in extreme environments near the sun. Geometric patterns might emerge from fracture mechanics or crystallization processes, producing regularity from natural physics. Thermal anomalies could reflect unusual composition or surface properties rather than active power generation. Activity variations might indicate rapid structural changes or complex sublimation chemistry beyond current model sophistication. But multiple independent signatures appearing simultaneously and exhibiting characteristics suggesting coordination or purposeful design would build a compelling cumulative case that eventually overwhelms natural explanations through sheer weight of compounding improbabilities. A trajectory change executed precisely at perihelion with timing and magnitude optimized for maximum orbital efficiency, combined with electromagnetic emissions detected during the maneuver, showing structured modulation. Thermal anomalies indicating onboard power generation at levels inconsistent with radioisotope decay or any natural process, and high-resolution imaging capturing geometric structure incompatible with random natural formation. That extraordinary combination of independent observations would strain natural explanations past any reasonable breaking point. Extraordinary claims require extraordinary evidence, but sufficiently extraordinary evidence eventually compels acceptance, regardless of how uncomfortable or paradigm-shattering the implications might prove for human civilization's self-conception. The observational campaign organized around this perihelion passage represents the most intensive, comprehensive, and coordinated monitoring effort ever directed at an interstellar visitor by the global astronomical community. Multiple space-based telescopes, including Hubble, James Webb, and various infrared platforms have scheduled precious observation time during the narrow, accessible windows, before and after solar conjunction, when the object remains visible despite sun proximity. Ground-based facilities spanning the globe, from major observatories in Chile's Atacama Desert to Hawaii's Mauna Kea Summit to Australia's dark sky sites, stand ready with coordinated observation plans to capture the object as it emerges from solar glare during its departure from the inner solar system. Radio telescopes, including massive arrays like the Very Large Array in New Mexico, and individual giants like Arecibo's replacement facilities, scan systematically for any artificial emissions across broad frequency ranges. Infrared sensors, both ground and space-based, monitor thermal signatures throughout accessible observation periods, measuring temperature distributions and searching for anomalies that might indicate internal heat sources or active thermal management beyond passive solar heating equilibrium. This represents an unprecedented, coordinated international effort, reflecting recognition within the professional astronomical community that, regardless of whether 3I/Atlas ultimately proves natural or artificial, it offers an extraordinary opportunity to study interstellar material up close, using instruments and analytical techniques unavailable during previous encounters with Oumuamua and Borisov. Each successive interstellar visitor receives more thorough characterization as observational capabilities improve and institutional coordination strengthens through lessons learned from earlier experiences. The data emerging from these intensive multi-wavelength observations will require painstaking, careful analysis before any definitive conclusions can responsibly be drawn and announced publicly. Raw images captured by optical telescopes need extensive processing through sophisticated pipelines to remove instrumental artifacts, cosmic ray hits, background stars, and countless other contaminating signals that corrupt measurements. Photometric calibration converts detector counts into physical units, accounting for atmospheric extinction, telescope throughput, and detector quantum efficiency variations. Astrometric reduction determines precise positions and velocities, correcting for parallax from Earth's orbital motion, aberration from finite light speed, and gravitational perturbations from solar system planets, affecting both observer and target. Spectroscopic data requires even more complex reduction procedures, accounting for atmospheric absorption lines that contaminate astronomical spectra, instrument response functions that vary with wavelength, scattered light within the spectrograph optics, and proper wavelength calibration using reference lamps and telluric features. Extracting physical information about composition, temperature, velocity, and other properties demands sophisticated modeling, comparing observed spectra against libraries of synthetic spectra generated from radiative transfer calculations incorporating atomic and molecular physics. This analysis pipeline takes substantial time, typically days to weeks, depending on data complexity and signal-to-noise ratios, before reliable results emerge suitable for publication and peer review. The modern information environment creates intense pressure for immediate answers and real-time updates as observations progress. But rigorous science requires patience for thorough verification before public announcements of preliminary findings that might require embarrassing retraction if subsequent analysis reveals errors or alternative interpretations. This fundamental tension between scientific methodology optimized for accuracy over speed and public curiosity demanding instant gratification creates communication challenges that astronomers navigate imperfectly at best. Remaining completely silent during extended data analysis periods allows speculation and misinformation to proliferate unchecked, filling information voids with increasingly wild theories that spread virally through social media before any corrective messaging can counter them effectively. But announcing preliminary findings prematurely before completing thorough verification carries different risks, potentially amplifying results that later prove erroneous when more careful analysis reveals instrumental artifacts, calibration errors, or natural explanations for initially puzzling observations. This damages institutional credibility and feeds public cynicism about whether scientific authorities can be trusted to report findings honestly, rather than promoting sensational claims for publicity. Finding appropriate balance between these competing pressures requires transparency about analytical processes, regular updates acknowledging ongoing work, while clearly distinguishing confirmed results from tentative interpretations subject to revision, and cultivating media relationships that allow nuanced communication, rather than forcing binary, confirmed, or debunked narratives. The broader context surrounding this particular interstellar visitor includes several critical factors worth examining in detail to understand how our detection capabilities and theoretical frameworks have evolved dramatically over just the past decade. First, the discovery rate of confirmed interstellar objects has accelerated far more dramatically than most planetary scientists predicted, even 5 years ago, driven by exponential improvements in automated survey telescope capabilities and sophisticated detection algorithms. Before Oumuamua's stunning detection in October 2017, professional astronomers had never confirmed a single interstellar visitor. Despite decades of theoretical predictions that such objects should exist in substantial numbers based on planet formation models and galactic dynamics calculations. The complete absence of confirmed detections before 2017 didn't necessarily mean interstellar visitors weren't passing through our solar system regularly. More likely, it reflected severe limitations in our observational infrastructure and data processing capabilities that prevented detection of these fast-moving, typically faint objects against the overwhelming background of stars, galaxies, and solar system debris. Survey telescopes before the modern automated era covered relatively small sky areas with long intervals between repeated observations of the same fields, making detection of transient moving objects extraordinarily unlikely unless they happened to pass directly through monitored regions during active observation windows. Even when captured in images, identifying these visitors among millions of asteroid detections required human analysis that couldn't possibly keep pace with data volumes. The revolution came through combination of wide-field survey telescopes like Pan-STARRS and Atlas that monitor huge sky areas every few nights, generating truly massive data streams measuring terabytes per night, coupled with machine learning algorithms trained to identify unusual moving objects automatically among the deluge of detections. These AI systems can process data volumes utterly impossible for human analysts to review manually, flagging candidates with unusual trajectories, brightnesses, or spectral characteristics for rapid follow-up observations before the objects move beyond detection range. This technological transformation explains why we've suddenly started detecting interstellar visitors at accelerating rates after decades of complete absence from the observational record. Now we've identified 3 confirmed interstellar objects in just 8 years: Oumuamua in 2017, Borisov in 2019, and 3I Atlas in 2024. Statistical extrapolation from this admittedly small sample size suggests these objects might pass within Jupiter's orbit at rates approaching 1 per year for objects larger than 100 meters diameter, with smaller objects arriving far more frequently but remaining too faint for detection unless they pass extremely close to Earth or exhibit unusual brightness through cometary activity. These numbers imply the interstellar population vastly exceeds the bound solar system population in the size ranges we can currently detect, a somewhat counterintuitive result that makes sense when considering that interstellar space has accumulated billions of years' worth of ejected debris from countless stellar systems across the galaxy, while individual stellar systems contain only their own formation remnants. Each successive interstellar visitor has exhibited compositional or behavioral peculiarities that sparked intense scientific debate about interpretation and implications. Oumuamua displayed anomalous, non-gravitational acceleration departing the inner solar system that didn't match standard cometary outgassing models, even after planetary scientists stretched assumptions about volatile composition and distribution to maximize predicted thrust. This acceleration anomaly led Avi Loeb and colleagues to propose exotic explanations, ranging from pure hydrogen icebergs that would sublimate without producing visible coma, to artificial light sails, pushed by solar radiation pressure. The mainstream astronomical community generally rejected these exotic hypotheses, preferring to attribute the acceleration to conventional outgassing, from volatiles that somehow avoided detection. But the controversy highlighted genuine puzzles about Oumuamua's nature that remain incompletely resolved. Borisov appeared more conventionally cometary in most respects, displaying obvious coma and tail, indicating active sublimation of volatile ices, but still exhibited compositional oddities when subjected to detailed spectroscopic analysis. Carbon monoxide abundance measured substantially higher relative to water than typical solar system comets display, suggesting formation in colder environments where carbon monoxide ice remains stable while water freezes out less efficiently. This compositional difference makes physical sense for objects formed around different stellar types, with different luminosities and radiation environments. But it demonstrates that interstellar visitors genuinely differ from solar system objects in measurable ways beyond just their hyperbolic orbits. They carry chemical fingerprints of their alien birth environments. offering precious direct samples of material processed under conditions fundamentally different from those that produced our own planetary system. Now, 3i Atlas arrives bearing its own distinctive set of anomalies that don't quite fit comfortable categories. The extreme carbon dioxide dominance detected through infrared spectroscopy by James Webb Space Telescope, showing ratios approaching 8:1 relative to water vapor, pushes beyond even Borisov's unusual composition into territory rarely, if ever, observed in solar system comets. Polarimetric studies reveal extreme negative polarization signatures, suggesting dust grain properties or size distributions outside normal ranges, though interpretation remains uncertain without better understanding of what materials might be present. Activity patterns show variations that some researchers claim appear inconsistent with simple solar heating models, though others argue the observations remain within plausible bounds given uncertainties about nucleus properties and rotation state. This pattern of successive interstellar visitors, each displaying their own peculiar characteristics, raises profound questions about whether we're seeing systematic differences reflecting genuinely exotic physics and chemistry operating in other stellar systems, or whether we're witnessing selection effects, where only the most unusual interstellar objects get flagged for intensive follow-up study, while more conventional visitors pass through unnoticed, or receive only cursory characterization. Statistical analysis of this question requires larger sample sizes than 3 objects can provide. But the trend suggests interstellar visitors as a class might systematically differ from solar system objects in ways beyond just compositional variations expected from different formation environments. One particularly intriguing possibility that deserves serious consideration, despite sounding like science fiction, involves the hypothesis that artificial probes might be deliberately designed to mimic natural objects to avoid triggering alarm among civilizations they're monitoring. If extraterrestrial intelligence has saturated the galaxy with surveillance infrastructure, as some researchers like Loeb suggest, those probes would logically incorporate camouflage as basic operational security. Making artificial objects appear naturally comet-like through deliberate outgassing systems, irregular shapes, and composition matching expected interstellar debris would allow covert observation of developing civilizations without revealing the observer's presence prematurely. This hypothesis is unfalsifiable in its strong form, since any observation showing comet-like properties could be explained as either natural or artificially camouflaged. But it highlights the epistemological challenges in distinguishing these possibilities based solely on remote observations. The institutional response within the astronomical community to detecting and characterizing interstellar visitors has evolved substantially since the chaos and confusion surrounding Oumuamua's unexpected appearance. That first detection caught the professional community completely unprepared, with no established protocols for coordinating rapid follow-up observations, no consensus frameworks for analyzing unusual trajectory data, and no agreed-upon communication strategies for managing public messaging about potentially paradigm-shifting discoveries. The scramble to organize observations before Oumuamua faded beyond detection range revealed serious gaps in international coordination infrastructure and highlighted needs for rapid response capabilities that didn't exist in 2017. Learning from those challenges, major observatories and research institutions developed formal protocols and standing agreements specifically addressing future interstellar visitor detections. These frameworks establish clear chains of communication, ensuring that discoveries made by one facility trigger immediate notification to partner institutions worldwide, enabling coordinated observation campaigns that maximize scientific return from fleeting opportunities. Data sharing agreements ensure that spectroscopic, photometric, and astrometric measurements collected by different teams get pooled into common databases accessible to the broader research community, rather than remaining isolated in individual institutional silos. This collaborative infrastructure means 3i/Atlas receives far more comprehensive and systematic monitoring than would have been possible during the Oumuamua era just 7 years earlier. Technological capabilities for detecting and characterizing these visitors continue advancing at remarkable rates. driven by both dedicated development efforts and spillover benefits from general improvements in astronomical instrumentation and data processing. Survey telescopes now achieve cadences in sky coverage that seemed impossibly ambitious a decade ago, scanning entire accessible sky regions every few nights with sensitivity sufficient to detect objects down to magnitude 22 or fainter under good conditions. Spectroscopic instruments achieve higher resolving power and broader wavelength coverage simultaneously, extracting more detailed chemical information from limited photon budgets collected during brief observation windows. Advanced adaptive optics systems correct atmospheric turbulence in real time, sharpening ground-based images to approach theoretical diffraction limits that were previously achievable only from space. Computational resources enabling sophisticated image processing, complex orbital modeling, and detailed spectroscopic analysis have exploded exponentially following Moore's law trajectories, allowing extraction of subtle signals buried deep in noise that would have been completely inaccessible to earlier generations working with more limited computing infrastructure. Machine learning algorithms trained on massive astronomical databases can now identify patterns and anomalies that human analysts would miss, automating classification tasks that previously required expert human judgment, while simultaneously processing data volumes that would overwhelm any conceivable human workforce. Each capability improvement shifts the boundary of what we can detect, measure, and understand, gradually transforming interstellar visitors from mysterious apparitions glimpsed briefly to objects we can study systematically with sophisticated analytical tools. Now let us turn our attention to the specific scenarios that could unfold during and after 3I Atlas Perihelion passage, examining each possibility with rigorous attention to what observations would constitute confirming evidence versus ambiguous signals requiring careful interpretation. The first and statistically most probable scenario involves purely natural behavior, entirely consistent with conventional cometary physics operating within established theoretical frameworks. The object passes perihelion following a gravitationally determined hyperbolic trajectory with only minor perturbations from asymmetric outgassing that match quantitative predictions from thermophysical models accounting for rotation, nucleus shape, and volatile distribution. Brightness variations follow predictable patterns based on solar heating intensity, varying with heliocentric distance and viewing geometry changing as observer-target sun angles evolve. No anomalous accelerations appear beyond what cometary jetting explains, through rocket thrust from sublimating volatiles escaping preferentially from localized active regions. Thermal emissions measured by infrared sensors match equilibrium temperatures expected for passive solar heating, given reasonable assumptions about surface albedo and thermal conductivity. Spectroscopic observations reveal composition dominated by common volatile species like carbon dioxide, carbon monoxide, water, and various organic compounds, with abundance ratios perhaps unusual compared to solar system comets, but still plausibly explained through formation around a different stellar type, with different radiation environment and chemical conditions. In this scenario, 3I Atlas joins the growing catalog of confirmed natural interstellar objects, scientifically valuable for what detailed characterization reveals about material processed in other stellar systems, but ultimately unremarkable regarding profound questions about extraterrestrial intelligence and technological civilizations. This natural outcome represents by far the most probable result based on our current understanding of how stellar systems form and evolve, ejecting enormous quantities of rocky and icy debris during chaotic planet formation epochs. Gravitational interactions among protoplanets scatter material throughout the nascent system, with some fraction receiving sufficient velocity kicks during close encounters with giant planets to achieve escape trajectories launching them into interstellar space. Most stars likely produce such debris clouds during their formation, meaning the galaxy has accumulated trillions upon trillions of wandering asteroids and comets over its 10 billion year history. Detecting these natural interstellar vagabonds represents exactly what improved observational capabilities should reveal, requiring no exotic explanations or paradigm-shifting implications about cosmic intelligence. The second scenario involves ambiguous anomalies that strain natural explanations without definitively proving artificial origin, leaving researchers and the broader public suspended in uncomfortable uncertainty. Perhaps the object exhibits acceleration slightly larger than outgassing models predict, even under maximally generous assumptions about nucleus properties. But the excess remains marginally within plausible ranges given substantial uncertainties about internal structure and volatile composition that cannot be directly measured. Perhaps thermal signatures show unexpected spatial or temporal patterns that don't quite match passive heating models, but could potentially result from unusual surface materials with anomalous thermal properties or complex sublimation dynamics involving multiple volatile species with different temperature thresholds. Perhaps activity variations occur on puzzling timescales that seem too rapid for thermal diffusion to explain, but might reflect rapid structural changes or explosive release of pressurized volatiles trapped beneath surface layers. In this ambiguous scenario, we would find ourselves with intriguing hints and frustrating incomplete evidence, unable to reach definitive conclusions, either confirming artificial origin or completely ruling it out based on available data. Each anomaly taken individually admits plausible, if somewhat contrived, natural explanations. But the cumulative pattern of multiple independent oddities occurring simultaneously raises uncomfortable questions about whether we're witnessing genuinely unprecedented natural phenomena or something more profound that our theoretical frameworks cannot accommodate. This outcome might prove most psychologically challenging, despite being entirely plausible scientifically, because human cognition strongly prefers clear resolution, distinguishing true from false, rather than prolonged suspension in epistemic uncertainty. The history of astronomy contains numerous instructive examples of observations that remained puzzling and controversial for years or decades before natural explanations finally emerged through theoretical advances or improved measurements. Quasars initially defied explanation because their extreme luminosities seemed physically impossible to generate from regions as compact as observations indicated, leading some researchers to propose exotic alternatives to conventional astrophysics. Only after decades of theoretical development did supermassive black hole accretion emerge as the natural explanation, confirmed through multiple independent lines of evidence. Gamma-ray bursts remained mysterious for 20 years after discovery, before distance measurements and detailed spectroscopy revealed their cosmological origin and connection to massive star death or neutron-star mergers. These historical precedents suggest patience and continued investigation eventually resolve most anomalies through natural physics. But they also demonstrate that prolonged uncertainty is a normal part of frontier science. The third and most consequential scenario involves clear, unambiguous artificial signatures that would fundamentally transform humanity's understanding of its place in the cosmic order. In this extraordinary outcome, 3I Atlas executes deliberate course corrections timed precisely for maximum orbital efficiency through exploitation of the Oberth effect, altering its trajectory by amounts and in directions impossible to explain through any combination of natural forces, including asymmetric outgassing, solar radiation pressure, or gravitational perturbations. Radio telescopes detect structured electromagnetic emissions originating from the object's precise position in space, signals exhibiting modulation patterns with information content clearly distinguishing them from any natural astrophysical source. Infrared imaging reveals persistent thermal anomalies, indicating substantial internal power generation at levels orders of magnitude beyond what radioisotope decay or any other natural process could sustain over interstellar transit timescales. High-resolution optical observations achieved through fortuitous close approach or dedicated interception mission captured geometric structure visible in direct imaging that proves completely incompatible with natural formation through gravitational accretion and random collision processes. Regular planar surfaces, precise right angles, cylindrical or spherical components with dimensional tolerances impossible for natural processes to achieve. Structural elements arranged in functional configurations serving obvious engineering purposes, rather than exhibiting the randomness characteristic of natural objects shaped purely by physics operating without intentional design. In this paradigm-shattering scenario, we would face the most profound discovery in human history, confirmed, unambiguous evidence of extraterrestrial technology actively operating within our solar system. The implications of such confirmation would extend catastrophically far beyond astronomy and planetary science, into literally every dimension of human civilization, culture, philosophy, and institutional organization. Philosophically, it would answer definitively one of humanity's oldest and most fundamental questions, about whether we're alone in the universe or whether intelligence represents a common emergent property of cosmic evolution occurring countless times across billions of stellar systems throughout galactic history. The answer that we're not unique, that technological civilizations exist beyond Earth and apparently possess capabilities for interstellar travel that we currently lack, would force radical reevaluation of human significance and cosmic context, and our species' potential future trajectory. Scientifically, confirmation of extraterrestrial technology would instantiate entirely new fields of investigation, focused on understanding alien engineering principles, attempting reverse engineering of observed capabilities where possible, and developing theoretical frameworks for how advanced civilizations might operate at technological levels potentially far exceeding our current achievements. Every scientific discipline, from physics to biology to computer science, would face paradigm shifts, as researchers grapple with existence proof that certain technological capabilities are achievable, even if methods remain mysterious. The mere knowledge that something is possible, rather than prohibited by fundamental physics, changes research priorities dramatically, channeling effort toward problems we know have solutions, rather than pursuits that might prove impossible. Theologically and philosophically, the discovery would force re-examination of humanity's place in cosmic significance, and the potential meaning or purpose of existence in a universe demonstrably populated by multiple intelligent civilizations. Religious traditions built on assumptions of human special creation or unique relationship with divine powers would face theological crises, requiring major doctrinal revisions or reinterpretations of core texts and beliefs. Some theological frameworks might accommodate extraterrestrial intelligence relatively easily, interpreting alien civilizations as additional examples of divine creation, expanding rather than contradicting religious narratives. Other traditions might face fundamental challenges if core doctrines depend critically on human uniqueness in ways that cannot easily reconcile with existence of other intelligent beings. Politically, confirmation would trigger unprecedented coordination challenges, as national governments attempt to formulate collective responses to presence of extraterrestrial intelligence, without established institutional frameworks or historical precedents for managing such extraordinary circumstances. Existing space law treaties provide no guidance for scenarios involving contact with alien civilizations or encounters with technological artifacts of extraterrestrial origin. New legal instruments would require emergency development addressing questions of territorial sovereignty over interstellar objects, protocols for attempting communication, liability frameworks for actions that might affect relationships with alien civilizations, and countless other issues that current international law simply doesn't contemplate. The United Nations might attempt to coordinate international response through existing structures like the Committee on the Peaceful Uses of Outer Space, but those institutions were designed for managing human space activities rather than extraterrestrial contact scenarios. Whether existing governance structures could adapt rapidly enough to address these unprecedented challenges, or whether entirely new international organizations would need creation, remains deeply uncertain. Geopolitical tensions and competing national interests would complicate any attempts at unified global response, with different nations potentially pursuing independent strategies based on their own calculations of risks and opportunities. Sociologically, reactions would span the complete spectrum of human emotional and intellectual response, from outright denial and conspiracy theories claiming government hoaxes, to apocalyptic fear about alien intentions and capabilities. to euphoric celebration of cosmic companionship, to pragmatic acceptance and curiosity about learning from advanced civilizations. Survey data collected by sociologists studying public attitudes toward extraterrestrial contact suggests roughly 40% of respondents find the prospect exciting and positive, 30% express concern or fear, and 30% report relative indifference or uncertainty. However, these proportions would likely shift dramatically upon actual confirmation, as abstract possibility transforms into concrete reality, demanding personal, psychological adjustment. Age demographics show interesting patterns, with younger generations expressing substantially more comfort with extraterrestrial contact scenarios than older cohorts, perhaps reflecting greater exposure to science fiction narratives that normalize such possibilities, or indicating generational differences in worldview flexibility. Educational attainment also correlates with response patterns, with higher education generally associated with more positive or neutral attitudes toward contact, though this might reflect confounding factors like science literacy, rather than education per se causing attitude differences. Cultural and religious background significantly influence responses, with secular populations showing more acceptance than strongly religious communities attached to doctrines emphasizing human uniqueness. But actual confirmation differs profoundly from abstract possibility in ways that opinion surveys cannot fully capture. The psychological adjustment required when theoretical becomes factual, when speculative transforms into observed reality, demanding integration into personal worldview, would challenge humanity in ways difficult to predict through pre-contact surveys of hypothetical attitudes. Historical precedents exist for how civilizations respond when encountering previously unknown others, from European contact with American indigenous peoples to modern globalization bringing distant cultures into direct interaction. But the cosmic vastness separating Earth from any extraterrestrial civilization makes direct analogies imperfect at best. Economically, confirmation of extraterrestrial technology would trigger massive investment increases in space capabilities as nations and corporations scramble to develop interstellar monitoring infrastructure, potential communication systems, and defensive capabilities against uncertain future scenarios. The space industry already represents hundreds of billions in annual global economic activity through satellite communications, Earth observation, navigation systems, and scientific research. Discovery that we're not alone would multiply those figures manyfold, as strategic imperatives shift dramatically. Defense establishments worldwide would demand capabilities for systematically detecting and tracking interstellar visitors, distinguishing natural objects from potential threats, and perhaps developing response options for various contingency scenarios. Scientific institutions would compete intensely for resources enabling dedicated research into characteristics, behaviors, and potential intentions of extraterrestrial visitors, and the civilizations that produced them. Private ventures would explore commercial opportunities ranging from space tourism, capitalizing on public fascination, to potential exploitation of any technological insights gained through study of alien artifacts. Stock markets would react with volatility as investors struggle to evaluate implications for existing industries and identify sectors likely to benefit from paradigm shift. Some analysts predict initial panic selling as uncertainty triggers risk aversion, followed by strong rallies in aerospace, defense, and technology sectors perceived as benefiting from increased investment. Culturally, the impact would propagate through every dimension of human creative expression, fundamentally reshaping art, literature, music, philosophy, and popular consciousness in ways that redefine how our species conceives of itself and its relationship to the broader cosmos. We currently exist in a psychological framework where humanity represents the pinnacle of known intelligence, the only technological civilization we can confirm exists throughout the observable universe. That perspective, whether consciously acknowledged or operating as unexamined assumption, colors everything from religious beliefs to political ideologies to personal meaning-making frameworks that individuals construct to navigate existence. Learning definitively that we share the cosmos with other intelligences, potentially far more advanced than ourselves, would require psychological and cultural adjustments comparable in magnitude to the Copernican revolution that displaced Earth from cosmic center, or the Darwinian revolution that connected humanity to broader biological evolution. But those previous paradigm shifts unfolded over generations and centuries, allowing gradual cultural adaptation as new worldviews slowly displaced older frameworks through generational replacement and educational reform. Confirmation of extraterrestrial technology would compress similar magnitude transformation into timescales of years rather than centuries, creating cultural whiplash as institutions and individuals struggle to integrate revolutionary new reality into existing belief systems faster than natural cultural evolution typically operates. Educational systems worldwide would face immediate pressure to update curricula at all levels, incorporating confirmed extraterrestrial intelligence into science classes, history narratives accounting for humanity's new cosmic context, and philosophical frameworks addressing questions about meaning and purpose in a demonstrably populated universe. Religious institutions would grapple with profound theological implications, requiring rapid doctrinal development without the luxury of centuries that previous major theological controversies enjoyed for resolution. Some religious traditions might adapt relatively smoothly, interpreting extraterrestrial civilizations as additional expressions of divine creation that expand rather than contradict core theological narratives. Others might face existential crises if fundamental doctrines depend critically on assumptions about human uniqueness or special relationship with divine powers that cannot easily accommodate existence of other intelligent beings created by the same cosmic processes. The diversity of religious traditions globally guarantees enormous variation in institutional responses, from seamless integration to fundamental crisis requiring major revision of core beliefs. Philosophers would revisit fundamental questions about consciousness, intelligence, meaning, and humanity's place in cosmic order with the concrete knowledge that other minds exist beyond Earth. Minds that might think in fundamentally different ways, shaped by evolutionary and cultural histories completely distinct from our own. What does consciousness mean when it emerges through multiple independent evolutionary pathways? How should we conceptualize intelligence when confronted with concrete examples potentially far exceeding human capabilities? Can meaning and purpose exist in a universe where humanity represents just one among countless intelligent civilizations, rather than unique cosmic observers? These ancient questions would acquire new urgency and entirely new contexts, demanding fresh philosophical analysis informed by empirical reality rather than pure speculation. The practicalities of confirming artificial origin present significant methodological challenges that deserve careful consideration. How does one verify extraordinary claims about 3I/Atlas when the object moves at tens of kilometers per second, departing observable range within weeks or months of perihelion passage? Independent replication represents the gold standard of scientific verification across all disciplines, but interstellar visitors don't cooperate by remaining stationary while multiple research teams conduct repeated observations. The evidence would necessarily consist primarily of data collected during narrow temporal windows that cannot be reproduced on demand, requiring trust in instrumental calibration, data reduction procedures, and institutional integrity of organizations reporting findings. Peer review processes designed for laboratory experiments, allowing repeated testing or astronomical observations of stationary objects that can be reobserved indefinitely, would need significant adaptation for unique, transient events that occur once and never repeat. How do you establish confidence in conclusions when independent verification means different teams analyzing the same, irreproducible dataset rather than conducting independent observations? What standards of evidence are appropriate when the phenomenon under investigation moves through observable space too quickly for the normal iterative process of hypothesis, observation, analysis, critique, and refinement that characterizes most scientific investigation? These epistemological questions lack clear answers from established scientific methodology. Historical precedents provide partial guidance while remaining imperfect analogies given the unique characteristics of interstellar visitor observations. The pulsar discovery already mentioned demonstrated how genuinely novel astrophysical phenomena can temporarily appear artificial until proper theoretical understanding emerges, cautioning against premature conclusions about extraterrestrial technology based on initially puzzling observations. The detection of the first exoplanets faced years of intense skepticism before accumulation of confirmations from multiple independent teams using different detection methods finally forced community consensus, accepting that planets orbit other stars. Extraordinary cosmological discoveries like dark energy, cosmic microwave background anisotropies, and gamma-ray bursts all underwent extensive verification periods involving multiple independent teams before scientific consensus solidified around revolutionary new interpretations. These examples suggest that confirming artificial origin of 3I Atlas would likely extend over months or years, even if initial observations show clear artificial signatures, requiring multiple independent analyses applying different methodological approaches, exhaustive investigation of alternative natural explanations, no matter how contrived they might seem, and accumulation of evidence from diverse observation types, all pointing consistently toward the same extraordinary conclusion. The professional astronomical community would demand certainty approaching absolute before endorsing claims with such profound implications, properly recognizing that extraordinary assertions require extraordinary supporting evidence, meeting the highest possible standards of rigor. The question of motivation becomes centrally important if artificial origin proves correct, because understanding why extraterrestrial civilizations might send probes to other stellar systems helps interpret observed behaviors and anticipate potential future actions. What objectives might such missions serve? Several possibilities deserve systematic consideration, each carrying different implications for what we might observe and how humanity should respond. First, scientific exploration represents perhaps the most optimistic scenario. Imagining that advanced civilizations systematically survey their galactic neighborhood, gathering data about planetary systems, stellar characteristics, biological diversity, and other phenomena of scientific interest, much as humans send robotic missions to explore our own solar system. Probes, serving scientific purposes, would likely operate passively, observing without interfering significantly with observed systems, collecting comprehensive data about diverse cosmic environments to build knowledge about galactic-scale patterns and processes. If 3I Atlas serves pure scientific exploration, we might expect minimal interaction beyond passive observation, just quiet data collection, followed by departure once survey objectives are completed. This scenario carries generally positive implications, suggesting we've been noticed by curious minds interested in understanding rather than exploiting or threatening us. However, even scientific observers might alter their behavior upon detecting technological civilizations, shifting from passive environmental monitoring to active intelligence gathering about potential peer competitors or future partners.